Greetings. We will go through the class 12 physics chapter 5 magnetism and matter exemplar problems. Okay. See, if you take a bar magnet, this is a bar magnet. This is called the axial line. Okay. And this one is the equatorial line. So if you look at the magnetic field in the axial line, so this is the formula. This is for the equatorial line. You will see the axial line will have double the magnetic field of the equatorial line. Okay. Now torque on a magnet in the magnetic field, that is mb sin theta. Theta is the angle between the magnetic field and the magnetic moment. D is the magnetic field. So this is the potential energy at any point on the magnetic field. Magnetic moment, magnetic field, the cos theta. Theta is the angle between the M and B. Okay. A toroid of N turns, mean radius or cross sectional A carrying current I. It is placed in the horizontal table taken as xy by the magnetic moment. Okay. It is 0. Otherwise, there will be a field falling in the 1 by 3 at a large distance. Okay. For toroid, the magnetic field inside that empty space is 0. So, magnetic moment is 0. Current enclosure is 0 in the empty space. Okay, in the chapter 4 you can go through this page and this page number. So you'll see magnetic field inside the toroid is 0, so the magnetic moment is 0. The magnetic field of the earth can be modeled by that of a point dipole placed at the center of the earth. The dipole axis makes this 11.3 the axis of the earth. At Mumbai, the declination is nearly 0. Then, okay, the declination varies from this west to east. Okay. Okay, this is the declination angle. This is the geographical north, and this is the magnetic north and south poles. Okay, this makes the angle 13.3. So this can also be like this. This magnetic dipole may also be like this. So this angle. So it is from east to from west 11.3 degree west, and this will be 11.3 degree east. So the declination is 11.3 degree west to 11.3 degree east. See here, this is the declination angle. Okay, this is the geographical north. Okay, so this angle. So if we place the dipole in this, so here also it can make that angle. In a permanent magnet at room temperature, okay, the domains, when you say permanent magnet, that is ferromagnetic material only will act as a permanent magnet at room temperature. Okay, so that will deals with the only domains. See here, substances which at room temperature retain that ferromagnetic property, that is ferromagnet only for a long periodic time, the permanent magnets. Okay, so the ferromagnet deals with the domains only, not at the individual molecules. Okay, consider two idealized systems: a parallel plate capacitor, large plates and the small separation, A long solenoid of length greater than the radius solenoid is ideally treated as a constant between the plates and the zero outside the capacitor plates. The magnetic field is constant inside the solenoid and zero outside. These idealized assumptions, however, contradicts fundamental laws as below. Okay, so this one, okay, it contradicts the gaseous law of magnetic fields because it says that the magnetic flux inside the thing is zero. That is, field entering and leaving the surface should be same as per the gaseous law. Okay, B dot delta ds is equal to 0. But here they are saying there is a field inside the solenoid. Okay, 10. So this is the gas law of magnetic field. Okay, the net magnetic field through any closed surface should be 0. Okay, there it is not 0. That means it is contradictory to the gaseous law. A paramagnetic sample shows a net magnetization when placed in an external field at a temperature. Okay, the same sample is placed in the different magnetic field at a temperature, then the magnetization will be. Okay, so we are going to use this formula: magnetization and temperature, Q is constant. Okay, and the magnetic field. So this is the given these things. Okay, they are asking what is M2. Okay, we are using this. So M1 by M2, the constant will cancel out. Okay, 1 by 2, then based on that you will get this 2 by 3. Okay, so this one 2 by 3. Okay, S is the surface of the lump of magnetic materials. The lines of B are necessarily continuous across that surface. Okay, the lines of H cannot all be continuous across the surface. Okay, this is H is the magnetic intensity, B is the magnetic field. The magnetic intensity varies inside the magnet and the outside. Okay. See, this is the like a bar magnet. See, look at the intensity magnetic field H here. So it is not continuous. Here more, here it will be less outside the magnet. Okay. The primary origin of the magnetization, it is because of the atomic currents and the spin of the electrons. Okay. Spin and orientation of the electrons mainly due to the unpaired electrons. That is the origin of the magnetization. A long solenoid of 1000 turns per meter and carries a current is just a arm core of that permeability. The core is located beyond the it is heated beyond the Curie temperature. That is, after that Curie temperature, it will lose the magnetic property. It will become a paramagnetic material. Okay. So the H field inside the solenoid is nearly unchanged because it is independent of the temperature. Okay, online. See here, this magnetic intensity depends on the number of turns and the current only. It is not depends on any temperature, so it is independent of the temperature. Okay, so is unchanged. B will be unchanged, but the magnetic field will decrease because of this permeability. What is susceptibility decreases with increase in temperature. Okay, so the magnetic field depends on the susceptibility that decreases with the increase in temperature. Okay, the magnetization in the core diminishes by a factor of this. Okay, after Curie temperature there is a Farad that will lose the magnetic. So 22 19. See the temperature after the Curie temperature, it will translate from ferromagnetic to paramagnetism. Okay, so paramagnetic, so that it diminishes the magnetic property. So you can also see this ferro and paramagnetic these coefficients. So here, so diamagnetic, paramagnetic. Okay, paramagnetic, this will be different. Susceptibility will change when you raise the temperature. The essential difference between the electrostatic shielding by a conducting shell and the magnetic shielding is due to the electrostatic field lines can end on charges and conductors have the free charges. Okay, the lines of B cannot end on any material and perfect sealing is not possible. Okay, so the B lines will be in a closed loop, whereas electric charges can end, electric field lines can end in other charges. The shells of high permeability materials can be used to divert the lines of V from the interior. Okay, this may be possible. V is directly proportional to the magnetic permeability. Okay, 180. So the B is here directly proportional to the magnetic permeability. Okay, so B equal to mu H. And the magnetic field on the earth is modeled by that of a point magnet dipole at the center of the earth. The angle of dip at any point on the, they are asking about the geographical equator. Angle of dip on the geographical equator. So I will show you what is the geographical equator. See the geographical equator and the ME, this is the magnetic equator. So the angle of dip can vary. Okay, here it may be more, here 0 and this may be less. Okay, negative, 0, positive. So can be 0 at specific points at the intersections. Okay, can be positive or negative, is bounded. Okay, a proton has the spin and magnetic moment just like an electron. Why then its effect is ignored, is neglected in the magnetism of the materials? 11. Because the proton has a higher mass than the electron, its spin is very less. See here, the mass of the proton is much greater than the electron. The spin of the proton is negligible as compared to the electron. A permanent magnet of shape of a thin cylinder of length 10 cm has a magnetization. Okay, calculate the magnetization current. The magnetization equal to magnetization current divided by the length. Okay, 12. Magnetization current divided by the length. Magnetization current. Okay, they are given. So they are asking what is the IEM. They are asking what is IEM. So magnetization is given, length is given. Though it is given in centimeter, we will convert into meter. So we will get the magnetization current 10 power 5 ampere. Okay. Explain quantitatively the order of magnitude of difference between the diamagnetic susceptibility and between the nitrogen and copper. Diamagnetic copper this one, and the nitrogen is this one. Okay, it depends on the density. Okay, nitrogen and copper. Okay, susceptibility directly proportional to the density. You see the density difference. So the susceptibility difference also varies accordingly from the given data. Hence, the major difference is accounted by for the density. Because of the density of the material varies, and the susceptibility also varies. From the molecular viewpoint, discuss the temperature dependence of the susceptibility of diamagnetic, paramagnetic, ferromagnetic thing. Diamagnetism is due to the orbital motion of the electrons developing magnetic moments opposite to the applied field. Diamagnetic is magnetic moment is opposite to the applied magnetic field. Okay, and hence it is not much affected by the temperature. Ferromagnetic is due to the alignment of the atomic magnetic moments in the direction of the applied field. As the temperature increases, the alignment is disturbed, and hence the susceptibility of both decrease with the temperature. Okay, paramagnetic, ferromagnetic susceptibility will decrease as we increase the temperature, but diamagnetic material is unaffected. The ball of superconducting material is dipped in a liquid nitrogen and placed near the bar magnet. In which direction it will move? What will be the direction of the magnetic moment? Superconducting material also diamagnetic materials. Okay, both nitrogen and nitrogen also diamagnetic. No unpaired electron. Nitrogen molecule. Okay, nitrogen molecule is a diamagnetic. There is no unpaired electrons. Superconductor also diamagnetic. Okay, now this will be move away from the magnet because of the diamagnetic property. It is repelled from the magnetic field. Magnetic moment will be opposite, that is from left to right. From here normally it will from south to north, but here in this case it will be north to south, left to right. See here how this diamagnetic material, how this repels this magnetic field. It will move away from stronger to weaker magnetic field. Okay, and the weaker part of the external field. Okay, it move from stronger to the weaker part of the external magnetic field. Move to the weaker part. Verify the causal of the magnetic field at a point dipole magnetic moment or the origin of the surface with the sphere of radius r. So here they have given, you can go through it from this diagram how they have write this. Three identical bar magnets are riveted together at the center at the same plane as shown here. The system is placed at the rest, slowly varying magnetic field. Okay, it is found that the system of magnet doesn't show any motion. Okay, it is not moving, it is stable. North south poles of the one magnet they are given north south pole determine the poles of the remaining two. Okay, there is no motion, there is no torque, okay, on the other magnet. So when you place like this will get attracted, but at this same time this side also it will get attracted, so it will get balanced. So there is no motion here. You see north south north south north south. So it will not move because the equal forces on the other side. Suppose we want to verify the analogy between the electrostatic and magnetostatic by experiment. Consider the motion of the electric dipole P in an electric field E, magnetic M in a magnetic field B. Write down the conditions and so that the two motions are verified to be identical motion. Assume identical initial conditions. Okay, so 5.18. See, this is torque on the magnetic field MB sin theta. Torque on this is the electric field. Okay, electric dipole in the electric field, this is magnetic dipole in magnetic field, this is the torque. They are saying these two torques are equal, so when you equate them, so MB equal to we will get but there is a electric field and a magnetic field relation using the velocity of light. So if you substitute for that, then you will get this relation. Okay, that is electric dipole equal to magnetic dipole by C. So electric dipole mounting magnetic dipole point by the velocity of light. A bar magnet magnetic moment M, moment of inertia I perpendicular to the length is cut. A bar magnet is cut into two equal pieces. Perpendicular to the, let T be the period of oscillation of the original magnet, that is a full magnet, about the axis through the midpoint, the perpendicular to the length. So in a magnet, what will be the similar period T for the each piece? Now a bar magnet it cut into two pieces. The full piece period of oscillation is T. They are asking for the individual pieces. Okay. Okay, this is the period of oscillation, 2 pi into moment of inertia divided by the magnetic moment, square root of moment of inertia. Okay, this now using moment of inertia, a magnetic moment. Now moment of inertia, this is from the book you can read, that is m L square by 12, that is the mass and this is the length. This is the moment of inertia formula. Okay, for it is like a rectangle, the bar magnet is a rectangle, so this is the formula. So after we cut into two pieces at half of the length, okay, half of the mass and half of the length, this will be the moment of inertia. and this is the ratio of the original magnet and to the cut magnet. Okay, so now they are asking so now for the T and for the T dash, that is cut, we substitute for the moment of inertia. After that you will get this. Okay, so now we will get a T dash, that is individual piece, that will be the half of the time period of the original oscillation. T dash equal to T by 2. That means less time means it will oscillate more, the frequency will be more. Okay, okay, it is equal to the T by 2. Okay, half of the original oscillation. Okay, this is the formula for the time period. 2 pi into moment is a magnetic moment and magnetic field. Use 1 Ampere's law of H continuity lines of B to conclude that the bar magnet lines of H run from the this one and okay. Okay, consider line B through the bar magnet. It must be a closed C. Okay, so H equal to B by mu naught from that formula from B by mu naught. So this is greater than 0. Okay, but the total closed loop, this will be 0 as per the Gauss's law. Sorry, Ampere in loop, in the loop H dot dl will be 0. So when this is 0 and this is greater than 0, then other will be less than 0. Okay, so from that you can make out H is okay. So this is that loop. Okay, verify that Ampere magnetic field point dipole of moment takes C in the closed curve running clockwise. Okay, this you can go through the, we have to use here, as I already showed you, there is a different formula for the axial magnetic field and equatorial magnetic field. This is for the equatorial one, this is axial one. Axial will double the equatorial one. So 21. So here is the diagram, and various gases they have given along the z axis, along the x axis, and this thing. So you can go through this answer. Okay. What are the dimensions of the susceptible magnetic susceptibility? Consider hydrogen atom, guess an expression for the susceptibility up to the constant by quantitative. Okay, you can go through this question and the answer. 5.2. Okay, you can go through this. Assume a dipole model of the Earth magnetic field, which is given by the vertical component of the magnetic field, and this is the horizontal component of the magnetic field. Okay, 23. They have given the, you can go through that answer. Okay. consider the plane S formed by the dipole axis, that is the magnet, dipole axis of the magnet and the axis of the earth. Okay, this plane is a two-dimensional plane they are making, formed by the dipole axis and the axis of the earth. Let P be the point on the magnetic equator and in S. Okay, magnetic equator and in S in this plane. Okay, let Q be a point at the intersection of the geographical magnetic equator. Obtain the declination deposit P. Okay, 24. Okay, this is the geographical equator, this is the magnetic equator, and dip is 0 in along the magnetic equator, any point on the magnetic equator. Okay, so the dip will be 0 on P and Q. So P dip is 0, Q dip is 0, but declination that will differ. So declination this along the geographical equator declination can be 0. Okay, see here, but here and the maybe 0, but here it is at Q 13.3 degree is the declination. At P the declination is 0 here. S needle will point both north. There are two current carrying platelets made each from the identical wires of length L. Okay, the C1 is the radius R1, C2 square. Okay, this is circular and this is square. They are so constructed that they have the frequency of oscillation, same frequency of oscillation when they are placed in the same magnetic field, carry the same current. Okay, same magnetic field, same current, same frequency, that is omega. Find the that A side, square side A in terms of R. So same frequency, same current, same magnetic field. Okay, so this is square of circle of radius R and the square A. So moment of inertia, this is you can read how it come, this moment of inertia formula. So here the magnetic moment is NIA. Okay, current, this is area, area of the circle pi r square. Number of loops is the length divided by the circumference 2 pi r, NIA. Okay, after a simplification here. So now this is the period of oscillation. Similarly for the M2, for this L by length divided by 4A, 4 sides. Then the area is A square. Okay, after simplification comes here. Okay, they are saying both the oscillation frequencies are same, that is omega 1 equal to omega 2. So when you equate it, you will get this formula. So here if you substitute the values for I and M, okay, M1, okay, this one, and I1 is this one, and M2 I2. Then after substitution you will get A equal to 3R. Okay, side equal to 3 times the R. Okay.